Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be focusing on how intermolecular forces can help control how solids form and their stability. So one of the first things we need to do is understand how different possible structures can be formed. And this is really going to be controlled by the type of attractive forces present. So this isn't just intermolecular forces like the van der Waals forces or ionic forces, but can also be like metallic bonds and covalent bonds, all of which will help bring atoms together into a large controlled solid structure. And one of the important things is it's very possible for solids to contain multiple types of forces. Remember, for example, everybody has dispersive forces, but you also have molecules like acetate, which will have covalent bonds holding the molecule together, van der Waals forces connecting the nonpolar regions, and ionic bonds holding together any negative charge. So one of the big things is figuring out which forces are at play, but mostly we're going to focus in on the strongest force present in any given material. So one of the more stable types of solids we can start with is going to be held together by our strongest of bonds, covalent bonds. If electrons are shared, those bonds don't want to break for anything. So these are generally referred to as network covalent solids or just network solids. And in general, they tend to have fairly rigid structures because those covalent bonds really don't want to bend or break. One of the more famous of which is diamond. So diamond is a network solid of carbon atoms held together in a tetrahedron. So every carbon atom is attached to 4 other carbon atoms in, again, a tetrahedral coordination where the central carbon will be sp3. And again, will really maximize the number of single bonds or bonds total that can be made. With a whole bunch of single bonds holding the system together, it's fairly wide distributed, but very strong. And as a result, diamond is very hard. That said, it's also brittle because there isn't a lot of give in that tetrahedral coordination. It is going to stay at those relatively fixed 109-degree angles. Not a lot of give, but as a result, very strong. But it doesn't bend, which means if you don't bend, you break when put under enough pressure. A good comparison of another type of network solid is graphite. So graphite is composed of large sheets of graphene. Graphene is essentially just a specialized name for a series of 6-membered rings, all held together. And we have alternating double bonds throughout, making a very resonance stabilized structure. A good way to think about graphene is what would happen if you took a benzene molecule and then just let it go on infinitely in any given direction. And as a result, it has a lot of resonance. So those electrons are moving around rapidly, which makes it a decent conductor, but it also makes it very strong. However, you'll notice that the covalent bonds only occur in one dimension. So each of these graphene sheets are layered on top of each other. So we have a network solid in 2 directions, but in the 3rd direction, up and down, it's just held together by London dispersion forces. However, when you have a lot of resonance or double bonds, this means the material is quite polarizable. So we can generate a good sort of set of London dispersion forces. So these different layers are held together fairly strongly because there's just so much of it. So again, this is a big sheet of Velcro being held together. However, it is worth noting because there are no covalent bonds in this direction, it means graphite isn't as hard as diamond. This is the reason why you can use graphite to, write things, because you're shedding off these graphene layers. That's what you're leaving behind. But as a result, it's a lot more flexible. You can have a large rod of graphite, which you can actually even bend a little because there's a lot more flex in these layers than in the much more rigid structure. So this really helps illustrate that even in network solids, sometimes London dispersion forces and other forces can play a big role. And the more you rely on those extra forces, the more you're going to gain flexibility, but you might not be quite as hard. Now, on the other side of the spectrum, you can have very few covalent bonds, but a lot of van der Waals forces. So the great example of this is water. And these are called molecular solids. I have small, discrete molecules held together by intermolecular forces. In general, the most stable of these solids will be held together by strong intermolecular forces. So if you can, hydrogen bonds gain a lot of stability. If you can't, you try and do kind of what graphite does and use a whole lot of dispersion forces and make size work in your advantage when you don't have a lot of individual strong bonds. Now, one of the big things that makes water so stable is that each water molecule will coordinate to 4 separate molecules. So again, you can treat this to a certain extent a little bit like a diamond, where you have a single center, in this case, a molecule instead of an atom, coordinating like a tetrahedron to 4 separate groups. However, because each of these connections isn't quite as strong, it won't be quite as hard as diamond. Again, ice does break quite readily, but ice also has a lot more flexibility than you'd get out of diamond because these connections are weaker. And there's always this big trade-off. Now, one of the things you can do is, instead of having individual strong polar bonds or hydrogen bonds, you can switch these up for a lot of weaker bonds, such as intermolecular forces. So another good example of a molecular solid would be benzene. So benzene, 6 carbon atoms, 6 hydrogen atoms. And again, because of this resonance in the center, it's very polarizable. It's easy to move the electrons from one side to another. And as such, it holds together fairly nice. So you've got a large molecule with enough polarizability, you can make things like London dispersion work to your advantage. And so, for example, benzene has a melting point of about 5.5 degrees C. So this is a higher melting point than water, because you're making the London dispersion forces, while individually weaker, on net can be just as good. However, one of the things that is worth noting is that as these IMFs become weaker, you're going to have a lot more softer material. So expect solid benzene to be a lot more soft than ice, because it's very easy to distort this lattice and rearrange. So in general, whenever I'm looking at a molecular solid, we're going to typically define it by whatever the strongest intermolecular force holding it together is. So if you're using London dispersion forces, this is going to be usually a nonpolar molecule. So noble gases, fats, organic solvents, these are going to be held together with lots of dispersion. So if you think about something like fat, it's going to be a lot more softer, a lot more flexible. If it's held together by general polar bonds, so think something like caffeine, you'll note not a hydrogen bond present, but a lot of polar groups, oxygen to carbon, nitrogen to carbon. This will generate positive and negative parts on the molecule. So again, won't be quite as good as if it's held together with hydrogen bonding, but can be pretty good. And you'll note that caffeine does make a decent crystal. On the extreme end, if you can use it, have a lot of hydrogen bonds. So this is sugar and water, largely held together by hydrogen bonds. Makes quite a strong lattice, but again, a little bit more rigid. Now, one of the things you may notice as the IMF gets stronger, we tend to have a much more rigid material. And you can take this to an extreme by going straight to an ionic solid. So ionic solids held together by charged ions, so those strong Coulombic forces, and will alternate positive, negative. So as a result, they're a lot more stable. They're much stronger intermolecular forces than you get for a molecular solid, often a little bit weaker than a network solid. But one of the big disadvantages of this arrangement is that it's a lot more brittle, because each of these anions has to stay far apart from each other. So green is chlorine, purple is sodium. So the chlorine needs to stay away from chlorine, sodium needs to stay away from sodium, because these like charges repulse. And as a result, they tend to form very consistent repeating crystal structures, as this is the way to best optimize those sort of connections. Similarly, it means that if I try and say, strike this with a hammer, it really can't bend, because we have these repulsive forces playing a key role. Instead, it will tend to break. And this is a very common feature you may be noticing. Now, similarly to kind of these ionic solids, you have metals. So whereas ionic solids are alternating cations and anions, one way you can talk about metals is thinking about each of the individual uh, atoms as a cation. So in this case, gold. So a gold plus one ion being surrounded by a moving sea of electrons that hold the system together. And because these electrons are a lot more mobile, it means you're going to have a lot softer of a metal, a lot softer of a substance. So gold is a lot softer than salt. But there tends to be very specific ways you can maximize these connections. And so you also, just like you tend to see in ionic solids, you tend to see very consistent crystal structures or crystal lattices with repeating units as the best way to optimize these systems. However, what exact crystal lattice you form will be highly dependent upon a number of properties, and usually it's the ratio of these properties. So how large is the system, how charged is the system, and how easy will each of these cations gain or lose an electron? How easily can those electrons flow? And as a result, you can have a lot of different crystal structures for metals. So some metals can adopt multiple crystal structures, but most prefer one form. And the structure of this lattice is going to dictate a host of properties. So this includes things like density, essentially how tightly packed can the system get. But it also can improve and impact properties like what color is the system. So how does light move into or out of this lattice? So what we're going to be doing over the next couple lectures is looking very specifically, how can I go ahead and arrange various systems into these set lattices? So we'll start with a simple case of working with metals where we only have one type of atom present, and we'll work our way out towards things like ionic solids where multiple different atoms may be present in a single system. Until then, take care.